Hello, and welcome to this hands-on lab using Oracle Machine Learning for Python on Oracle Autonomous Database. I'm your instructor, Mark Hornick, Senior Director, Oracle Machine Learning Product Management. We're looking forward to taking you through this series of labs that introduce features of Oracle Machine Learning for Python. Just to summarize, these are our goals for today's session. Take a test drive of Oracle Machine Learning for Python that's available with Oracle Autonomous Database, where you'll get to explore different aspects of in-database machine learning through a Python API using OML notebooks. You'll work interactively with your data to build, evaluate, and apply machine learning models, including the new automated machine learning or AutoML capabilities. Included in many of the labs are try-it-yourself exercises that will help you to check your understanding. To set expectations, these labs focus on the Python API only. OML for Py also provides a REST API, which will be added to a later version of this lab. We should also note that this session is not intended as an introduction to machine learning or details of specific algorithms. Rather, we are highlighting the functionality and use of OML for Py as it supports data science projects. If you're interested in introductory material for machine learning, please check out our recorded OML office hours at the link provided here. For our agenda today, we start off with getting everyone access credentials to the Autonomous Database and OML Notebooks environment. I'll then introduce Oracle Machine Learning, followed by an overview to the labs that we'll be working with. Before working through each lab, I'll give a brief introduction to some of the content covered in that lab. We'll be taking questions throughout in the chat and Q&A. As we go through the labs, if you have questions for the broader audience, please enter them into the Q&A. If you need specific help with the environment or lab, please enter your question into the chat for our panel of experts. We are fortunate to have several experts with us today. Feel free to contact them directly in chat if you have any questions. Let's get started with access credentials. While you're getting your credentials, here's a brief video introducing OML for Py.
So you have enterprise data managed by Oracle Autonomous Database, and you have data scientists who use Python. Data scientists need data. The database has data. What if we could bring these two great technologies together? What if data scientists could use familiar pandas data frame functions to explore, prepare, and analyze database tables and views as though they were pandas data frames transparently? What if data scientists could build machine learning models at scale directly in the database using those same familiar pandas data frame proxy objects and a native Python API to in-database algorithms, and leverage automatic machine learning, AutoML, as a productivity tool? What if data scientists could couple this with additional Python packages like scikit-learn and matplotlib to develop and deploy solutions with user-defined functions stored in the database, and then, using REST endpoints, deployed easily using database-spawned and managed Python engines, where functions and data are automatically loaded, even with parallel options? Well, with Oracle Machine Learning for Python and Oracle Autonomous Database, data scientists can do just that. So what are you waiting for? Learn more at oracle.com/machine-learning and take OML for Py for a free test drive in Oracle Autonomous Database.
Okay, so we'll get started with the introduction. Let's briefly touch on the broader Oracle Machine Learning product family that supports data science projects. Oracle Machine Learning provides interfaces for three popular languages: SQL, R, and what is the focus of this lab, Python. For interaction with Autonomous Database, we provide OML notebooks based on Apache Zeppelin with SQL and Python interpreters. Oracle Data Miner is a SQL developer extension that enables users to create, schedule, and deploy analytical workflows through a drag-and-drop user interface that is compatible with on-premises and database cloud service databases. Oracle Machine Learning for Spark provides machine learning in the big data environment with native scalable algorithms, as well as Spark MLlib algorithms included in the same framework. Also coming soon are Oracle Machine Learning AutoML UI, a no-code user interface that automates model building, selection, and deployment, and Oracle Machine Learning Services, a REST-based service for model deployment and management, along with cognitive text. On Autonomous Database, Python users access OML for Pi via OML Notebooks, which provides a collaborative user interface based on Apache Zeppelin technology, further extending Autonomous Database as a data science platform. Data scientists, analysts, developers, and DBAs can use both SQL and Python in the same notebook, using the most appropriate language for the problem at hand. They can also view notebook changes by team members in real time, interactively. These same data science team members can explicitly share notebooks and templates. Users can version notebooks as well as schedule notebooks to run at a set time or a repeating schedule. By virtue of being included in Autonomous Database, machine learning functionality is automatically provisioned and managed. Through OML Notebooks, users have access to the in-database algorithms and analytics functions to explore and prepare data, build and evaluate models, score data, and deploy solutions. So now let's focus on OML for Pi. Oracle Machine Learning for Python leverages the database as a high-performance computing environment, manipulating database tables and views through Pandas data frame proxy objects with overloaded functionality that is translated to SQL transparently behind the scenes. This enables exploring, transforming, and analyzing data faster and at scale by keeping data in the database, while allowing the use of familiar Python syntax to manipulate database data. The in-database parallelized machine learning algorithms are exposed through a natural Python interface. With OML for Pi, users can build more models on more data and score large volume data faster, taking advantage of autonomous database optimizations, including autoscale. Data scientists benefit from automated data preparation, partitioned model ensembles, and integrated text mining. This can result in increased productivity, while at the same time the powerful in-database algorithms are made more accessible to non-expert users. Data scientists and other users can create user-defined Python functions and manage these as scripts in the database. Python objects can also be stored in the database, as opposed to being managed in flat files. These features also facilitate collaboration across the data science team, enabling efficient handoff of data science work products from data scientists to application developers for immediate deployment. Moreover, these user-defined functions can be run in a data parallel or task parallel manner, for example, to enable scoring native Python models at scale. Results from these user-defined functions can contain both structured and image results and be accessed via Python and REST APIs. Oracle Machine Learning for Python also supports automated machine learning, or AutoML, which not only enhances data scientists' productivity, but also enables non-experts to use and benefit from machine learning. AutoML can help produce more accurate models faster through automated algorithm and feature selection and model tuning and selection. In addition, model explainability, or MLX, provides model-agnostic identification of important features impacting model predictions. AutoML and MLX are core technologies developed by Oracle Labs. Here's a quick summary of the 6 labs included in this session. The first lab is quite straightforward. It's just intended to get you started with the Python interpreter and OML for Pi in OML notebooks. The second lab focuses on selecting and manipulating data using the transparency layer. Here you'll use data frame proxy objects that map to database tables and views. The third lab focuses on using the in-database algorithms for model building and making predictions with the resulting models. The fourth lab shows how to store Python objects in a database using the data store capability. In the fifth lab, you'll use embedded Python execution, which allows you to run user-defined Python functions in Python engines that are spawned by the database environment. Lastly, the sixth lab focuses on automated machine learning, where you will identify the top algorithms and features and perform automated hyperparameter tuning. Throughout these labs, there are paragraphs labeled "Try it yourself." These are exercises for those of you feeling up to the challenge. The answers to the Try It Yourself exercises are in the notebook Try It Yourself Answers. So let's jump in. In your Chrome or Firefox browser, go to the URL provided with your credentials. Then log in with the provided username and password. This will bring you to the home page for OML on Autonomous Database. Then click Notebooks, which will bring you to the list of notebooks. Click on Lab 1, Getting Started with OML for Pi. By now, you're in the first notebook. Let's get oriented to some of the buttons or controls available to you in this Zeppelin-based notebook environment. To the right of the notebook title are a series of buttons that apply to the overall notebook. You can run all paragraphs in the notebook, show or hide code and output, clear all the output, clear the notebook of paragraphs, leaving a single paragraph, and export the notebook as a JSON file. There is a search code button, but the browser search Control F also works just as well. Next, you can see how many users are connected to this notebook. Recall that multiple users can have the same notebook open for collaboration. This allows you to see which users have the notebook open as well. You can get a list of keyboard shortcuts to the Zeppelin environment, and the interpreter bindings, which allow you to specify the priority level of the connection to the database. While we explain this in the notebook, you shouldn't need to change the setting for today's labs. In an individual paragraph, you will see the paragraph status. You can click the triangle to run the paragraph, show or hide the code editor and output, and access more features. These features include various visualization options, positioning of paragraphs, among other features. So now take the next 10 minutes to run through this notebook and get acquainted with OML notebooks and OML for Pi. To get you started on the first lab, let's sign in to OML notebooks. From here we can click on Notebooks to see the list of notebooks available to us. And we're going to start with Lab 1, Getting Started with OML for Pi. Here you can read through the various content we have provided. This repeats some of the material that was in the slide presentation. As you go further, you can try running a markdown paragraph. You can copy this, paste it into the paragraph, and then click Run. And we see that we have the result. If you want to hide the editor, you can do that, and there you have your text. To connect to the Python interpreter, we specify %Python at the beginning of the paragraph. And when we click Run, this spawns a Python engine on the back end and passes the script that we have here for running it in that Python engine, returning the result. The first one takes a few seconds because it actually is starting up that Python engine. Subsequently, as we'll see here, when we go to import the OML package, it's almost instantaneous. Next, if you'd like to check if you're actually connected to the database, you can run oml.isConnected, and so we see here this returns true. So take the next few minutes to go through the rest of this lab to acquaint yourself with OML notebooks and the basics of paragraphs. Let's move to Lab 2. Select and manipulate data using the transparency layer. The transparency layer of OML for Pi provides the foundation for leveraging in-database performance using Pandas data frame proxy objects and overloaded functions that translate the requested behavior to SQL transparently. Users can take advantage of database column indexes, query optimization, parallelism, and table-level partitioning, which can greatly improve performance on database table operations. Here we see how we can create a table from a Pandas data frame using oml.create, specifying the table name we wish to use, in this case Boston. If the table already exists in the database, we can use the function oml.sync and specify the table name we wish to retrieve. This produces a proxy object that we can then use to invoke familiar Pandas functions like shape, head, and describe, and even take advantage of Python syntax for splitting data into train and test sets. These overloaded functions, in effect, translate desired functionality to SQL for in-database processing. The transparency layer supports a range of functionality. These functions support data transfer and proxy object-related behavior. They include functions for creating persistent and temporary tables, getting proxy objects, dropping tables, listing the names of proxy objects available in the workspace, and getting a cursor object that can be used with the Oracle Database Connectivity Package, CX Oracle. This cursor can be useful when users want to update data in an existing table or invoke SQL functionality more explicitly within Python. Note that the OML for Pi interface doesn't allow actual data to be updated or deleted, but manipulate it and to be able to create new tables in the database. This example shows the use of in-database scalable aggregation using the overloaded crosstab function. We first get our proxy object to a table called onTimeS, and then ask to count the distinct values in the destination column. This request effectively gets translated into a SQL query with a group by clause on the dest column. Upon running this function, we can see the result type is an OML data frame object. When we invoke the head function, we retrieve the first few rows of the result. Note that results may be large themselves, so rather than pulling the entire result to the client, requiring both time and memory, the result remains in the database with a proxy object returned for subsequent use. In its first release, OML for Pi provides these overloaded functions that operate on OML data frame proxy objects. The goal for Lab 2 is to become familiar with creating and using data frame proxy objects for exploring and transforming database tables and views. Take the next 15 minutes to work through the steps of this notebook. So for the second lab, we'll click on Lab 2, OML for Pi Transparency Layer. This opening paragraph explains the contents of the lab. The first thing we'll do is import libraries and then create an OML data frame proxy object. So we're starting up the Python engine, and from there we're going to create a temporary data frame. We're loading the iris data from scikit-learn datasets, preparing that data so that we can actually create a table that contains both the predictors and the target. And we see this result returned here in the Zeppelin table output. We're using the z.show to implicitly retrieve those rows and display them in the Zeppelin environment. Z is a special object that we introduced in the previous lab. We can list the available Python transparency layer functions using this script. Next, we'll do some data manipulation, selecting table columns, filtering rows, and the like. So take the next few minutes to go through the remainder of this lab. Moving on to Lab 3, using in-database algorithms and models. With respect to machine learning algorithms, OML for Pi version 1.0 provides a natural Python API to the in-database algorithms listed here, supporting classification, regression, clustering, attribute importance, anomaly detection, association rules, and feature extraction. The in-database algorithms naturally support automatic data preparation, partitioned model ensembles, and integrated text mining. Users can extend this set of algorithms with those provided in Python's scikit-learn package. In-database models produced through the Python API can also be accessed using the SQL API. In this example, we illustrate using the in-database support vector machine algorithm. After importing SVM from the OML package and getting our proxy object, we specify the desired outlier rate in the dictionary variable settings. In the SVM function, we specify that we want to do anomaly detection, that we want a linear kernel, and then we pass the settings. Anomaly detection uses the special one-class support vector machine algorithm, and the outlier rate indicates our selectivity for anomaly detection. We then invoke the fit function to train the model and view the model details by displaying the result object. Partitioned models allow users to build a kind of ensemble model with automatically produced submodels, one for each partition. This automates a typical machine learning task and can potentially achieve better accuracy through multiple targeted models. The submodels are automatically managed and used as a single model. When you go to make predictions, you only need to leverage the top-level model. The proper submodel is automatically chosen based on the row of data to be scored, which includes the partition value or values. For Lab 3, the goal is to learn how to build and score using in-database machine learning algorithms, as well as some of the other model-related functionality. Step 5 touches on the model-agnostic feature importance ranking of predictors. It's fairly straightforward, so take about 10 minutes to complete this lab. So now click on Lab 3, OML for Pi Algorithms. And as before, we'll import some libraries. And then we're going to build a regression model using a generalized linear model. For data, we're going to use the OML sync function, and this time we're going to pass in a query in the query argument. This allows us to specify an arbitrary SQL query for returning data that we'd like to have as our pandas data frame proxy object. We'll do the same thing with the demographics data frame and then merge those data, joining them, into the cust df that we'll use for the rest of this example. Again, using z.show, we can see the first few rows in our data set, invoking the overloaded head function. From there, we're going to split the data randomly into sample for training and for test. Notice the Python syntax that we have using the overloaded split function and passing those results into train and test variables, the 60% and 40% respectively. And from there, you'll go on to build the generalized linear model. So take the next few minutes to complete this lab. Next is Lab 4. Use data stores to store Python objects. The data store allows users to save Python objects, including OML for Pi proxy objects, in the database as a named entity, and then load them back into Python memory across client sessions. A data store can contain one or more Python objects, making it very convenient for passing data into user-defined functions. There are two main use cases for data stores. The first use case preserves Python objects across client sessions. For example, for temporary tables created using the OML push function, and in-database models created using the OML for Pi API. The data store is used to preserve such proxy objects across Python and database sessions. Otherwise, these objects are dynamically dropped when the database connection is terminated. Normally, with Python objects, when your Python engine shuts down, all of the objects in memory are lost, unless they've been saved, normally to a flat file. OML for Pi mimics this behavior for proxy objects, such as those of tables, views, default named model objects. The second use case involves using a data store to pass data and objects to user-defined Python functions, especially when dealing with non-scalar objects for REST invocation, such as native Python machine learning models. Here we see the range of functions supporting the data store functionality for storing Python objects. We can save one or more Python objects in a named data store, list the existing data stores available to the current session user, describe the contents of a named data store, load the objects from the data store into Python memory, delete one or more data stores from the repository, or delete specific objects within a given data store. Users can also grant or revoke access privileges to other users. The goal for Lab 4 is to learn how to store and manage Python objects, both native and from OML, in the database using data store. Take the next 10 minutes to work through this lab. Click on Lab 4 for the OML for Pi data store. This opening paragraph gives an introduction as well to the data store concept. And as always, we will load our libraries. And then we're going to create a few pandas data frames and load them into Autonomous Database so that we can use them in combination with our data store examples. The first proxy object we'll get is using OML sync from a view defined on the iris table. Next, we'll create a temporary table using the diabetes dataset, where we push that into the database. And next, we'll create a temporary table, Boston, using OML push as well. Next, we want to save these objects into the data store, and we invoke oml.ds.save. And we're going to pass in the iris as oml_iris and the Boston temp as OML Boston. So take the next few minutes to finish up this lab. Let's move on to Lab 5, running user-defined functions using embedded Python execution. Embedded Python execution provides a variety of features on Autonomous Database. For one, the database environment controls and manages the spawning of Python engines to run your user-defined Python functions, and can automatically load data into that function. The result from your function can be returned as tables, accessible via data frame proxy objects. Both image and structured content can be returned from your functions. You can leverage third-party packages that are provided with OML for Pi in your user-defined functions, for example, to build scikit-learn models. The embedded Python execution infrastructure enables running your function in a data parallel and task parallel fashion. This enables what one calls embarrassingly parallel use cases. Your user-defined Python functions can be stored and managed in the database script repository. And although we won't be using it in this lab, you can invoke your user-defined Python functions using a REST interface for application integration. Here is the list of embedded Python execution functions that you can use for invoking your user-defined Python functions. DoEval is the simplest and runs your function in a single Python engine and returns the result. TableApply also runs your function in a single Python engine, but passes in the data referenced by your proxy object as a pandas data frame in the first argument of your function. RowApply enables data parallelism. It partitions data into chunks of rows and runs your user-defined Python function on each chunk, using one or more Python engines spawned and controlled by the database environment. GroupApply also enables data parallelism. It partitions database data by the column or columns specified by the index parameter and runs the user-defined Python function on each partition using one or more Python engines. Lastly, IndexApply enables task parallelism. It runs your user-defined Python function the specified number of times, passing the index value as the first argument to your function, using one or more Python engines as specified in the parallel argument. Embedded Python execution facilitates production deployment of user-defined Python functions. Here we show using the Python API for running a user-defined Python function in parallel that builds a scikit-learn linear model and returns that model. In this example, our goal is to build one model for each species in the iris dataset. Using the GroupApply function, it takes a proxy object, in this case the iris proxy object, and the index column we wish to partition the data on, in this case the species column. We pass in the user-defined function and the number of Python engines we want spawned to run this function. There are several variations in how embedded execution can be used, and this example just scratches the surface. For example, user-defined functions can be stored by name in the Python script repository in the database. The same name is used when invoking such functions through the REST API or granting access privileges to other users. As we mentioned, the script repository is used to store your user-defined Python functions as scripts in the database. You can grant and revoke the read privilege to a script, list the available scripts, load script functions into the Python environment, and drop the script from the script repository. Here we see the range of script repository functions for managing Python user-defined functions. The goal for Lab 5 is to learn how to run user-defined Python functions in database-controlled Python engines and work with the Python script repository. Take the next 15 minutes to complete this lab. For Lab 5, click on the OML for Pi Embedded Python Execution Lab. This opening paragraph describes much about what is available in embedded Python execution. So as before, we'll first import our OML for Pi library. And then we're going to create our iris table using OML create. A best practice workflow for working with embedded Python execution is to first develop your Python script interactively using the Python command line. From there, you take your script and turn it into a Python function. Then, you validate that function by running it in Python directly. If necessary, you can adapt your function to use the data store if you're passing non-scalar arguments, for example. Then you run your function by passing it as an argument to the embedded Python execution API. Next, store your function in the script repository. Then run your function by name in the Python API and validate it in the REST API prior to providing it to application developers. So take a few minutes to work through the rest of this lab. Let's move on to our last lab, Lab 6, Use AutoML. Our objectives for OML for Pi AutoML are to eliminate repetitive tasks such as model building and evaluation through automation, with the goal to increase user productivity, both for expert data scientists and non-experts. AutoML applies machine learning to the machine learning process itself, using what we call meta-learning, to automatically zero in on the right algorithm, features, and algorithm settings necessary to build high-quality models without resorting to exhaustive search. Such automation helps to make machine learning more accessible to a broader audience, while reducing the compute time and cost required to get to the desired result. Let's take a look at automated machine learning in OML for Pi. As we noted, AutoML increases data scientists' productivity while reducing overall compute time. It also enables non-expert Python users to leverage machine learning, in part because they don't need to be experts in the modeling process, the range of algorithms with their data preparation requirements, or understand each algorithm's hyperparameters. OML for Pi's AutoML consists of 3 steps. With automated algorithm selection, the goal is to identify the in-database algorithms likely to achieve the highest model quality. Using meta-learning, AutoML leverages machine learning itself to help find the best algorithm faster than with exhaustive search. With automated feature selection, the goal is to denoise data by eliminating features that don't add value to the model. By identifying the most predictive features and eliminating noise, model accuracy can often be significantly improved with the side benefit of faster model building and scoring. Automated model tuning tunes algorithm hyperparameters and can significantly improve accuracy while avoiding manual or exhaustive search techniques, which can be costly both in terms of time and compute resources. Our goal for Lab 6 is to become familiar with the AutoML workflow and related functions. Note that some AutoML function invocations can take a few minutes to complete, since a lot is going on behind the scenes. So please be patient and allow the paragraph to complete before moving on to the next. Take about 15 minutes to complete this lab. Let's move on to the last lab, 6, OML for Pi AutoML. The opening paragraph gives you a brief description of what's in this lab. And as before, we will start off by importing the various libraries we require. We're going to be using the wine dataset, and since this is already stored in the database, we're simply going to invoke oml.sync. And we can see that we have 178 rows, 14 columns, and these are the columns that are provided in this dataset. Next, we'll prepare the data for automated algorithm selection by separating the target from the predictors. From there, we will create our algorithm selection object, indicating that we want to do a classification problem, use the score metric of accuracy, and also enable a degree of parallelism at 2. Next, we'll select the algorithms that are most likely to perform well on this data set. By specifying k equal to 4, we're indicating that we'd like to see results for the top 4 algorithms. And when you view the results, you see that we have not only the ranked algorithm, but also its corresponding score metric. So with that, take the next few minutes to complete Lab 6 with AutoML. So where do we go from here? We covered a lot of territory in this set of labs. You've explored how to prepare data using the transparency layer, build models, and make predictions using in-database algorithms. You've seen how you can store Python objects and manage them using the OML for Py data store. We saw how you can run user-defined functions using embedded Python execution in a variety of ways, including returning images and structured content. And working with automated machine learning to streamline the process of selecting algorithms, selecting features for model building, and tuning algorithm hyperparameters to get the quote-unquote best model. For more information on Oracle Machine Learning and Autonomous Database, check out these links. Also check out our office hours where we conduct webinars on all things Oracle Machine Learning. Note that Oracle Machine Learning is integrated with Oracle Analytics Cloud, and there are a wide range of examples that you can draw upon. Thank you for joining us for this hands-on lab on Oracle Machine Learning for Python.